では、定刻になりましたので、第13回目の計算科学技術特論 A を始めていきたいと思います。本日は理研の淳さんに講義をしていただきます。本日の講義は英語で講義をしていただきます。質問は日本語でも大丈夫です。So, the talk is Dr. Jun from Liken. So, the title of his talk is Parallelization of Molecular Dynamics. So, please start.
Thank you for the introduction. So I'm very sorry to present in English, but please do not hesitate to ask me in Japanese. And here I'll talk about how we can parallelize MD simulation using, in particular, on many supercomputers, including Fugaku. First, I'll briefly explain MD. What is MD? And what is the main problem in MD? So in molecular dynamics, we first describe energy and force from classical molecular mechanics force field. So for each atom, we predefine the parameters related to the force and energy calculation. And if we calculate the force, then you can update the state according to the equation of motion. So for example, if you see this one, if we calculate the force, then you can update momentum and coordinate in this way using a very small finite time step. And finally, we can obtain the trajectory of coordinates according to the simulation time. And this trajectory is again used for ensemble generation. And based on the generated ensemble, we can calculate various kinds of physical properties related to statistics to obtain the reliable thermodynamic quantities of a target system. In fact, long-time MD simulation is very important. But unfortunately, the basic time step is very small. So here, I'll just explain one MD integration scheme named velocity ballet. So at time t, we first evaluate the force. And if we evaluate the force, then we update momentum from t to t plus half delta t. And using this momentum, we can update coordinates from t to t plus delta t. And if we obtain new coordinates, then we can calculate force at t plus delta t. And using this force, we update the momentum from t plus half delta t to t plus delta t. And again, update the momentum. And using this momentum, we update the coordinates. And from the updated coordinates, we evaluate the force again. And we repeat this procedure over and over again. This is the basic scheme of MD integration. And in MD simulation, in fact, the problem is the time step is too small. In the case of all atom MD simulations, one time step delta t is limited to just 1 or 2 femtoseconds due to vibration motions. On the other hand, many biologically meaningful events occur on the timescale of milliseconds or even larger. And to obtain the MD simulations using these timescales, we need to accelerate energy and force calculation. So this is some example. For molecular vibration, it occurs from the femtosecond to picosecond level. And protein side chain motions, it's from picosecond to nanosecond level. And main chain motions of proteins, for example, it occurs from nanosecond to microsecond level. And protein folding phenomena can be observed after performing microsecond level, and or even millisecond level. And large protein global motions, you can observe it by performing more than millisecond level. So this is a very difficult problem in MD. In particular, if you want to observe folding or protein global motions, somehow acceleration of energy pulse or some kind of enhanced sampling scheme is very important. So this is the history of biological MD simulations until now. The first biological MD simulations was done in 1977. At the time, there was no water molecules. Only they performed very small protein simulation named PPTI. And it is the time scale and target system size is increased according to the hardware and software development. And recently, not recently, but 10 years ago, in USA, one group made a special MD machine named Anton. And from this one, some MD milliseconds MD simulation is available for a small protein. And in our group, also on K computer and Ocupress packs, you could simulate for the system consisting of around 100 million atoms and 1 billion atom system. And I think this one is the world's largest MD simulation target system size until now. And anyway, to increase the MD simulation timescale and system size, efficient parallelization is very important. And before going to the parallelization, I'll briefly explain the potential energy in MD. Here, I'll explain in all atom case. So potential energy usually consists of these terms: bond, angle, dihedral, improper dihedral, and non-bond interactions. Yeah, bond is just vibration between two atom pair, and angle is bending, and dihedral is the angle between the first three, the plane formed by the first three particles and the plane formed by the last three particles. And in some cases, you also consider improper dihedral angle calculation. All of these calculations, the computational cost is just order of n, where n is the number of total particles. In fact, these are not so time consuming. But problem is the non-bonded interaction. In MD, usually we include van der Waals and electrostatic as non-bonded interaction. And the computational cost becomes order of n squared. And this is the main bottleneck in MD calculation. And to evaluate non-bonded interaction in practical point of view, we consider periodic boundary condition with infinite images. For example, this is the original system. But in real calculation, for each particle, we make the copy of the same system. And we consider the interaction between particles with not only inside of this system, but also the periodic image systems. And in fact, this one is very time consuming, and usually we introduce the truncation of van der Waals interaction. Because van der Waals interaction has the 12th and 6th power over inverse of distance, it is saturated very rapidly. So for this particle, instead of calculating all particle pairs, we introduce the range of particles that there is some colorful distance from this target particle. So here you can introduce some threshold value that have the interaction, and we can greatly reduce the computational cost using this scheme. But this way is applied only for van der Waals interaction. For this electrostatic interaction, this is just one of all interaction, and we couldn't apply this kind of threshold. Then, how we evaluate the electrostatic interaction? we decompose the electrostatic interaction into real space and reciprocal space interaction. And the real space interaction, like van der Waals, the pairwise distance, the interaction range can be limited, and it can introduce the same threshold value like van der Waals. And in the case of reciprocal space interaction, we can introduce the cutoff values on the reciprocal space. So somehow we can greatly reduce the total computational cost using this way. And until now, I briefly explained the energy evaluation in MD. And in this MD, in fact, the key concept of parallelization is just acceleration. So by using 16 CPUs, for example, and if we can just increase the speed about 16 times, then somehow we can perform very long time simulations. And if we can also decompose the target system size in each CPU using this kind of decomposition, we can reduce the memory size on each CPU. Then you can easily increase the target system size. But to do this, we need to consider two things. One is the small amount of computation in one process. So we need to optimize the MD program such that each CPU just computes the interaction at a minimal cost. And another important thing is the small communication cost. So somehow, in some cases, we need communication between different MPIs, for example. But the key point in parallelization is how to minimize these communication costs. And next, I will go into the parallelization. So this one is just the parallelization of in general. So I think most of you are familiar with parallelization. So I will just briefly explain. Here, you can consider possible shared memory parallelization. And one of the example using shared memory parallelization is OpenMP. In this case, every processors the shared memory. And in program, in C or Fortran, we can use this comment, pragma or OMP. Then you can perform the shared memory parallelization. So the key point in here is that all processors share the data in memory. So this processor has the information of this processor, the memory. And for efficient parallelization, one of the key points in shared memory parallelization is that processes should not access the same memory address. So if this processor access to this point, then this processor, we need to assign that this processor does not access the same memory. And in fact, this is only available for multi-processors in a physical load. So this way is not applied for multiple nodes, but just a single node. Another parallelization is the distributed memory parallelization. One of the examples is MPI. In this case, every processor has their own memory. And each processor does not know the information of other processors. And in this MPI, when we start the program, we need to assign these comments: MPI init, MPI comlength, MPI comsite. This is defined initial procedure and it's not changed during the computation. So it's less flexible than shared memory parallelization. And to understand the information of other processor, we need to send or receive the data via communication. And in this case, the amount of communication should be minimized. And nowadays, almost supercomputers and almost programmings, you are using hybrid parallelization by combining MPI with OpenMP. And this one is applied for multiple nodes, and in each node, there are multiple cores. And in each node, you can share the memory. And in fact, this one is the most useful for using very large number of processors. So in this case, at the very initial status of the programming, you should write the MPI init, MPI com length, MPI com size. You should define the MPI related parameters. And during MD simulation or any computation, for every do loop or for loop, we can assign the shared memory parallelization. And another kind of low-level parallelization is SIMD, single instruction and multiple data. I think nowadays, this one is one of the most important to accelerate the computation. So if we consider 3 arrays, one has arrays of A and B and C, and A has, let's assume that 4 elements, A1, A2, A3, A4, and B has 4 elements and also C has 4 elements. We want to obtain the element of C just adding the element of A and B. And in this case, we first obtain the C1 from the addition of A1 and B1. And next, we can obtain C2 by adding A2 and B2. So to obtain the 4 elements of C, we need 4 addition operation. But if we apply SIMD, then A1, A2, A3, A4 is considered just as one element in, and the from B1 to B4 is also identified as one. And you can just obtain from C1 to C4 just one addition. And in fact, in most MD programs, this SIMD becomes one of the most important topics to increase the performance. Then now, I'll move to MPI parallelization of MD. In particular, I'll explain non-boundary interaction in real space. So one of the easiest parallelization scheme is to use the replicated data approach. In this case, each process has a copy of all particle data, and each process works only part of the whole works by proper assign into the loops. In do loops, let's see this one. We have a do loop of I index and do loop of J index. So this is just a particle pair interaction between I and J. Here, we can make use of it by defining the my MPI length and by defining total number of MPIs. We can just change this do loop to this way. Then we can reduce the computational cost of each MPI very easily. After doing this one, we have energy and force data, only partial data. So finally, we need some reduction scheme in MPI. So in this case, let's see that. So for each particle, here, for each particle I, they have a size of J list in this way. A second one has, and third, fourth, fifth, and has in this way. And if we assume that if we have 4 MPI processes, then the first index of 1 can be evaluated on MPI rank 0, second one by MPI rank 1, third one MPI rank 2, and so on. In this case, problem is that MPI rank 0 has the largest amount of computational cost, and MPI rank 3 has the least amount of computational cost. So in this case, perfect load balance is not well guaranteed in this parallelization scheme. This is the problem of this method, MPI parallelization scheme. And moreover, reduction with communication, reduction cost is very large. And this one prevents the usage of a larger number of MPIs. So nowadays, there are some MD programs using this scheme, but if you consider high performance MD simulation, no MD programs are using this kind of parallelization. And even for this one, we can make use of hybrid parallelization by combining MPI with OpenMP. For example, the first do we distribute over MPI processors. And we can just change this to in this way by combining the new index, by making a new index combining MPI rank and my OpenMP ID. This is one way. Or the first do we can distribute over MPI rank, and the second do can be parallelized by OpenMP. So there is no unique way of parallelization, but I can just say that even with this replicated data method, we can consider many kinds of efficient parallelization by efficiently combine MPI with OpenMP. And in fact, in Genesis MD software, one simulator named AT9 is making use of this scheme to accelerate the speed, even using this kind of parallelization scheme. And the good thing of this approach is that easy implementation. You don't need to consider the overall structure so much. We can just assign the simple change of do loop in this way or in this way. But it has many problems. First of all, parallel efficiency is not good. There is no perfect node balance. And communication cost is not reduced by increasing the number of processors. This is one of the main problems. And you can parallelize only for energy calculation. And this one means that in MD, after evaluating energy and force, we need integration procedure. And in fact, integration scheme itself is not parallelized using this one. We only parallelize the energy and force calculation. And another problem is that it needs allowable memory because each processor has the global data, all of the data. And nowadays, almost MD software is making use of domain decomposition scheme as parallelization. In this case, the whole simulation space is divided into subdomains like this one. Here is the different colors. And we assign MPIs for each subdomain. And each MPI only consider the energy and force action only related to this subdomain. So the MPI assigned to this one have no idea of interaction of these particles in this region. They only calculate the particle pairs in this region. But in some cases, we need to calculate the interaction between particles between here and here. So to do this, the particle pair interaction between different domains, we need MPI communication among neighboring processors. So this processor has some communication between this one, this one, this one, and this one. So in this scheme, each subdomain needs to have the data of not only this subdomain, but additional buffer region. And this amount of buffer region is dependent on the threshold values in van der Waals and real space electrostatic energy calculation. And in this domain decomposition scheme, the interaction between particles in different subdomains, like between here and here, or here and here, this one should be carefully dealt. If not, we can easily have some errors in energy or force calculation. And one of the features in this domain decomposition is that the size of subdomain and this buffer region is decreased by increasing the number of processors. So if we increase the MPI, then the memory usage of each MPI is greatly reduced. And because of this, we can perform MD simulations of very large system. So if we see the good thing and bad things of this scheme is that the first good thing is that parallel efficiency is good. You can reduce the computation cost by increasing the number of processors. And another good thing is that you can easily parallelize not only energy and force, but also integration. In fact, everything can be parallelized. And because of this, we can make use of this scheme for a very large system. But problem is that implementation is not so easy. And domain decomposition scheme is highly dependent on the potential energy type. So here, I mentioned the all-atom case with van der Waals and electrostatic energy calculation. But if we change the potential energy, or if we change the parameters of a threshold, then the domain decomposition scheme cannot be well applied. And in some cases, the particle distribution is not uniform, and good performance cannot be obtained well without considering good load balance scheme. And for such non-uniform particle distributions, there are several methods. Here I'll say two examples. One is the tree method, where subdomain size is adjusted to have the same number of particles. So in some cases, there are many particles, and in some region, there is very small number of particles. And the region of small number of particles, we assign larger size. And for more dense part, we reduce the the subdomain size. And another way is to make use of Hilbert space filling curve. So here, we make a curve that traverses all of the domain simulation system. And according to this curve, you can assign you can decide the subdomain system. And if we compare the replicated data and domain decomposition parallelization schemes, as for the computation, they have the same order. But in the case of communication, domain decomposition has much less amount of communication. And even for the memory, domain decomposition has much small amount of memory. So here, I only explain the MPI parallelization of real space with colorful values. Now I'll explain the MPI parallelization in reciprocal space calculation. So electrostatic interaction can be decomposed into 3 parts using Ewald scheme. The first one is real space, and second one is reciprocal space, and there's additional self-energy. This one is just constant, so you can neglect the computational cost of this term. And this real space, you can introduce the threshold or cutoff values. And we can assign the parallelization explained in previous slides. And in the case of reciprocal space interaction, in fact, this one is approximated as this way, some kind of prefactor with test Fourier transformation. And in reciprocal space interaction, one of the most important thing to parallelize is the parallelization of this test Fourier transformation. So the overall computational procedure is like this. First, we have a charge on your space. Then you convert to charge on grid space. And charge on grid space, we perform the fourth FFT. And we obtain the FFT data on the grid. And using this one, we can calculate energy. And by multiplying some prefactor, and by performing inverse FFT, we can evaluate the post values. So in each step, we need one forward FFT and one inverse FFT for reciprocal space calculation. And before explaining the parallelization of FFT, I think it's better to briefly explain the MPI all-to-all communication, because in FFT, in most parallelization libraries and programs, people are using this MPI all-to-all comment. If you see this matrix and assume that you have an element like this one from A1 to A4 column, B1, B4 column, and so on, and just assume that processor 1 has the data of A1 to A4, and process 2 has the data from B1 to B4, and so on. If we perform MPI all-to-all communication, then process 1 has the data of A1, B1, C1, D1, and process 2 has the data of A to B to C to D2, and so on. So MPI all-to-all is the same as matrix transpose. And in FFT, we are only make use of this communication command. And in FFT parallelization, there are three schemes. One is the simplest one, slab or one-dimensional decomposition. In this case, each process is assigned a slab of size n by n over p for computing FFT on n by n grids on p processors. So this is the whole grid data, and we just define by dividing the g dimension or x dimension. So in this case, the scalability is limited by just the number of grids. And this number of grids should be divisible by the number of processors. So this one is good for using very small number of processors. But if you wanna use very large number of processors, then I do not recommend to use this parallelization scheme. So for one dimensional port FFT, we have the scheme in this way. First of all, in this direction, we perform FFT. And then we perform FFT in this direction. In this case, because each processor has the global data of this direction, no communication is necessary. And after performing FFT in this direction, next you want to perform FFT in this direction. But in this case, this processor has only partial data, does not have the global data of this one. But in performing FFT, we need global information in this direction. So in this case, we perform MPI all-to-all, such that every processor has the data in this way. Then you can perform FFT. So for the FFT, we need only one MPI all-to-all communication. So good thing is that this is fast if we use very small number of processes, but it has the limitation of larger number of processors. And another very frequently used parallelization of FFT is 2D or pencil decomposition scheme. In this case, each processor has the data of this pencil-shaped one. So first of all, each processor has the data like this, and you first perform FFT in this direction, and next you want to perform FFT in this direction. But this processor, every processor does not have the global data in this direction, so we need all-to-all communication among three processors of the same color. So in this case, for example, these three processors need to have the MPI all-to-all communication to have the data in this way, and to have the data in this way, and so on. Then you can perform FFT in this direction. And next, to perform FFT in this direction, we again perform all-to-all communication among processors having the same color. So these three processors have some MPI all-to-all communication and so on. And finally, you can have the data in this way, and you can perform FFT. So using this decomposition scheme, we need two MPI all-to-all communication. So this one has 5 steps. One-dimensional FFT in the X direction, and all-to-all communication, and Y direction, all-to-all communication, Z direction. And this one is slower than 1D decomposition if we use small number of processes, but we can increase the parallelization when you use the larger number of processes. And another thing is the three-dimensional decomposition, which is the parallelization scheme used in Genesis MD software. In this case, each MPI have the data of this cube of each cube. And to perform FFT in this direction, these four processors have the all-to-all communication and have the data in this way. So in this case, they have the global data in this direction. And after performing FFT in this direction, this shape is to the cube again. And to perform FFT in this direction, we assign MPI all-to-all communication among four processors in this direction and have the data in this way. And back to the original shape. And all-to-all communication again to obtain this shape and to perform FFT in this direction. So in fact, this parallelization scheme requires more communication. So one-dimensional decomposition, we need only one all-to-all communication. And two-dimensional, we require two MPI all-to-all communications. But in this case, we need to do 1, 2, 3, 4, 5 all-to-all communications. But we can reduce the number of processes involving in each communication. So here, the number of cubes is 64. So here I assumed 64 MPIs. But the maximum number of processes involving in communication is just 4. So for this one, I just assign MPI all-to-all among these 4 processors and so on. So good thing is that we can greatly reduce the number of processes involving in each communication. So this one is very useful when you perform the large scale MD simulation using very large number of processes. So next, I'll show some, as some case study, I'll show some parallelization scheme of Genesis on Fugaku supercomputer. So MD software Genesis has been developed in Riken, and the main director is Dr. Yuji Sugita. It allows high-performance MD on parallel supercomputers like K, Fugaku, Tsubame, and so on. And it is free software under LGPL license. It is started from 2009, and Kobe team in Riken started between 2010 and 11, and I came to Riken around this time, and I started to develop parallelization of Genesis. And now, from the initial release of Genesis, now there are many updates of Genesis MD software. And recently, the optimization version for Fugaku is released in the last year. So in Genesis SP9 simulator, we are making use of domain decomposition. So first of all, the simulation space is divided into subdomain according to the number of MPI processes. So here, I assume that 9 MPI processes. And each subdomain is again divided into the unit domain named cell. So in here, in each subdomain consists of 16 cells. And particle data are grouped together in each cell. So for each particle, we assign them as making use of a cell index. And communications are considered only between neighboring processes. So this one only have the communication with these processors, this one and this one. And in each subdomain, we make use of OpenMP parallelization. So in Genesis, for each particle data, we on memory, we define saved in this way. So particles in the same cell are also close to each other in the memory. So we found that this kind of optimization is very important to make use of memory in an efficient way. And even in domain decomposition, there are many different schemes. And among various schemes, we developed the so-called midpoint cell method. So in this case, the intersection between particle pairs, we define the intersection point as a midpoint cell. So for example, let's consider the particles in cell A and cell B. And in fact, particle here is saved in this MPI, and particles in A cell is in different MPI. And the pairwise interaction between particles between two, we need to assign in this MPI or this MPI. And we decide the MPI processes to evaluate the interaction between particles in different subdomains, just making use of the midpoint cell. So here, particles in A and particles in B, the midpoint cell of A and B is this one. So we assign the MPI process having this cell. So here, particles between A and B is done by MPI with this subdomain. And in some cases, this kind of midpoint cell is not uniquely defined like this one. For this particle C and D, midpoint can be either this one or this one. And we decide the midpoint cell by considering the number of particles of this one and this one. And we assign the interaction to increase the load balance as much as possible. So in this case, each MPI has the data of this subdomain and also additional population like this way. And with hyperparallelization, here, if we just assume 16 MPI processors for this system, and here I'll just focus on the MPI having this subdomain. For hyperparallelization, before performing hyperparallelization, we need data of this population. So first, we communicate the data of this one and this one. And next, we import the data from upper processors of this one and this one. So this MPI has the data of this subdomain and the population. And then we make an index of cells. So here, this processor has 16 cells. And for each particle pair, we first make a cell pair list, 1, 2, 1, 3, 1, 2, 2, and so on, this way, and check if each particle pair, if the midpoint cell is in this domain or not. For example, 1, 1, of course, the midpoint is 1 and in this domain, a yes, and so on. But in some cases, 1 to 5, somehow here there's no unique definition of the midpoint cell for this cell pair. So as I explained in previous slide, I decided considering the load balance. And here somehow we decided as our midpoint cell. So we calculate here. But in some cases, 1 to 6, we found that it is not calculated in this subdomain, but maybe calculated in MPI with upper subdomain. And after making this midpoint cell checking, only for yes part, we parallelize by OpenMP. So this cell pair list is again distributed by OpenMP. And in this way, we could obtain good parallelization scheme. So for each cell pair, we make an atom index of the first cell and second cell. And then for each atom index on the first cell, we make a list of atom index in the second cell to be calculated in non-bounded interaction. So let's see. This one is just a simple pseudocode. We make all cell pair list. And for each cell pair, we define the first cell index and second cell index. So in previous example, if the cell pair is 1, 1, then I am sorry, let's see this one. Then here, the first cell might be 1 and second cell might be 2. And we make a do loop of the first cell index here, this one. And then we decide the atoms within the cutoff values from the second cell. So for each part, for example here, the first particle in the first cell have the interaction of the first, third, and fifth particle in the second cell. And the second particle in first cell has the interaction of second, fifth, sixth, seventh particles in the second cell. And in this way, you calculate the particle pair interaction. And in fact, this way was very useful when we perform MD on K computer. And we also expected the similar performance on Fugaku supercomputer. But in fact, we found that there are many things to be reconsidered on Fugaku supercomputer. One is the optimization of Fugaku is quite different. So here I'll show two examples. To loop of I and j, I is from 1 to 16 and j is 1 to 16. In fact, we can combine this ij index as 1 and we can make a do loop of from 1 to 256. Just theoretically, this algorithm 1 and algorithm 2, they are identical to each other. There is no difference in the computational cost. But we found that on Fugaku, this algorithm 2 is much better. It's because of the upon the waiting time for each do loop. So on Fugaku, to allowing the SIMD command in the most inner do loop, they have some kind of optimization procedure. And such optimization procedure is not negligible at all. And to minimize such waiting time to perform the each do loop, we found that the most inner do loop should be as long as possible, and the call of do loop should be minimized. So in this way, we found that by making a large do loop of the most inner do loop part, we can reduce the upon the waiting time quite much, and we can increase the performance much better. So in your program, maybe there are many small do loop like this one. For example, 1 to 3. Or in Fortran, you can also write something like this from 1 to 3 in this way. The loop length is very small, just 3. So in this case, we found that not to optimize is better when you use Fujitsu compiler. So in this case, we just assign the no SIMD comment for each to-do. So then in this way, we could increase the performance. So if I say again, one thing is to make a to-do length as large as long as possible. This is one thing. And for small to-do, it's better not to optimize. So it's better to assign no SIMD comment. And on Fugaku, until now, I previously explained that we make a cell index and atom index. So usually, for each cell, we make an index in this way. This is the original array structure in Genesis. And on Fugaku, we first changed the array structure not to make use of this cell index, but the global atom index in this way. So this one, 1 to 3 is XYZ coordinate, and 1 to MX atom is this local coordinate in each cell, and 1 to N cell is the cell index. This one is the original array structure, but on Fugaku, just to optimize the performance, the first thing we did is not to use this separated cell and atom index, but combine the index in this way. The reason is to increase the to-loop length as much as possible. In our original scheme, we calculate the particle pair interaction based on cell pair interaction. So for example, let's consider the first and second cell pair. And this one is the atom index of the first cell, and this the atom index in the second cell. Somehow we assign the interaction based on this circle. Separately, for one cell pair, we also have the similar kind of interaction list, and so on. In our original program, these things are done separately. But on Fugaku, in our cases, we combine them together. And the first atom of the first cell has the to-do of not only this, but also this one. So here, in the original program, the to-do of the first particle in the first cell has 3. And to-do length of the first particle in the first cell in this interaction is 3, and so on. But we make a to-do index of all of these things at the same time. So the main point is to increase the to-do length on Fugaku as much as possible by combining each cell pair interaction into one interaction, by making a change of this atom index in this cell to global index in this way. And the first particle have the interaction with 15 particles here, and second 15 particles. So to-do length becomes much larger by making a to-do of it in this way. Previously, it has just 3, 2, 2, 2. But by combining as one to-do, we can increase the to-do length much more. So in the previous pseudocode, we make a cell pair index, and we make a first cell, second cell, and make a to-do of the first particle of the first cell, and particle of the first cell, and to-do of the particle index in the second cell. But here, for each cell and each atom, we just make a index, larger index of the combined we make an index of these things. So by changing the algorithm from the cell pair to in this way, we can obtain much larger to-do lengths. Here, this one is the distribution of the to-do lengths in this scheme. In the original scheme, the maximum to-do length is just 100, and most have the to-do length around from 20 to 40. But in the new algorithm, we increase the most inner to-do length around, up to 1000, and the most one is around 500. So in this way, we can reduce the operation waiting time greatly. And another consideration in our optimization of Fugaku is to assign prefetch much more easily. So basically, when you calculate something, then at the same time, we make a prefetch of the next calculation. So this one, in fact, increase the performance slightly. This until now is the optimization way of Genesis MD software as for the real space calculation. As for the reciprocal space calculation, as I said in previous slide, we make this kind of procedure. From charge in real space, we make a charge on grid space and FFT, energy calculation, inverse FFT, and finally force calculation. And on Fugaku, in fact, this procedure is also not negligible at all. And I explain how to optimize these two procedures on Fugaku supercomputer. We first need to understand the charge grid data evaluation in Ewald scheme. So for each particle on real space, we can consider some grid space with some limited range. And the real space charge data is converted to the grid data on this grid point with different prefect ratio. And the amount of neighbor, so how much they affect the grid, depend on the splines order. So until now, we have the charge data of not only this subdomain, some also buffer region. From this one, the charge on this region may generate charge grid data on this region. And among them, we just select the charge grid data in this subdomain region. And we discard the charge grid data on this blue region. But good thing is that we don't need any communication at all in this procedure. And that's why we used this scheme for K computer. But we found that this scheme cannot be well applied if we use a large spline order with large grid spacing. So if we increase the spline order and grid spacing, then we can reduce the grid points in FFT, and we can greatly increase the performance on FFT by reducing the grid points. But we found that using such a small number of grid points of FFT is not available in our scheme, because to obtain the grid data of this one is not sufficient. We need much larger real space region. So in our cases, we change the scheme of charge grid data evaluation on Fugaku. First of all, we don't consider the charge grid data from this buffer region. we only generate charge grid data only from this subdomain region. Then we may generate the charge grid data in this way. And after that, if we generate this one, we send the information of this one to lower processor and send this one to upper processor. And we have a grid data in this way. And finally, by just local communication, we have the final charge grid data. So in this case, communication is necessary, but communication is very local. And in previous cases, in fact, to generate very large number of charge grid data and discard it is a time-consuming one. But in our cases, we can, just considering the charge on this space, not the buffer space, we can reduce the overall amount of computation. Using this way, we could greatly increase the performance on Fugaku supercomputer. And I will explain the result of the computational cost on Fugaku. Here, algorithm 2 is the original scheme in Genesis developed on K computer. And this algorithm 3 is the new algorithm developed on Fugaku. In fact, one integration step, the computational time is less than half. And the pairist generation is also true. The new algorithm increased the performance using the same number of processors. So it increased the performance more than twice. And as for the disperse space number inflection, we found that by increasing the grid spacing, which means that the number of grid points is half, but instead of increasing the spline order to keep the accuracy, we found that the new scheme greatly increased the computational cost and greatly reduced the computational costs and greatly reduced the computation time less than half. But if but we found that, for example, if we compare this new scheme and original scheme for a large number of processors, in fact, they are comparable. So we found that our new scheme is particularly good for a small number of processors. But if we use large number of grid points and large number of processors, then the original scheme is comparable or even better than the new scheme. So using this kind of development, we could obtain the good scaling of conventional MD. Here, we increase the system size twice by increasing the number of processors. And finally, we could simulate 1.6 billion atom system. And using a small number of grid points, we can obtain good so we can obtain around 75 parallel efficiency ratio compared to 16 nodes. And in fact, the this computational result, so 3.3 nanosecond per day for 1.6 billion atom system, I think we found that this is much better than the world best performance result until now. For example, for this system, we obtained this result 8.3 nanosecond per day. But if I see the other programs' performance until now for very large system, we found that the best one is around 5 or 6 nanoseconds per day for 1 billion atom system. So this another one is a strong scaling result. Yeah, for 1.15 billion atom system, we obtain around 12 nanoseconds per day performance, and we found that this one is around twice better performance than existing MD software. And this is a summary. So might be my explanation minus sufficient in some part, then please give me a question. So in this lecture, I mentioned the parallelization, including MPI and OpenMP and hybrid. And I said that parallelization of MD should be almost parallelization scheme is mainly by domain decomposition with parallelization of non-boundary interaction. And key issues in parallelization is how to minimize communication cost to maximize the parallel efficiency. And also, as I show in Fugaku example, hardware-aware optimization is a very important point. So yeah, my lecture is up to here. Thank you for your attention.
Thank you very much. ありがとうございました。